Think about your morning today. I mean, if you're anything like me, the first hour of your day was probably a masterclass in dodging chaos.
Oh, absolutely.
Right. Like you are sidestepping a dog toy left in the middle of the hallway. You are lunging to catch a falling coffee mug before it shatters on the tile.
Swerving around that massive pothole on your commute.
Exactly. We live our entire lives in this incredibly messy, unpredictable, three-dimensional soup of objects. Everything is constantly spinning and deflecting, just crashing into everything else.
It's exhausting just thinking about it.
It is. And from the outside, it just feels entirely random. But then, you step into the world of theoretical physics, specifically the way we structure academic standards, and suddenly that messy soup just, well, it evaporates. You find yourself staring at a landscape that is perfectly ordered.
Yeah.
It is almost unnervingly pristine.
It really is. You are basically taking reality and stripping it down to its absolute barest bones. You remove the dog toy, the coffee mug, the pothole, the air resistance, the friction, and what you are left with is just pure, unadulterated mechanism.
And that stark contrast is exactly what we are exploring today. Welcome to the deep dive. We are looking at something incredibly unique for you today. The source material we have is, it's short.
Very short.
I mean, remarkably short, literally just a few sentences long. It is an excerpt titled Principles of Momentum, Impulse, and Collision Dynamics. And technically, it's an academic standard labeled PS.PHY.3.
Right, and it might look like, a single dry bullet point on a ethics syllabus, but the conceptual weight it carries is just massive.
Yeah, our mission today is to decode this highly specific framework. We're going to figure out how these few lines of text actually build a step-by-step master plan for understanding physical reality. So, okay, let's unpack this.
Let's do it.
Because to the untrained eye, reading a standard that says, analyze the motion of objects based on the principles of conservation of momentum and impulse in one dimension, well, that sounds like a surefire way to induce a coma.
I mean, yeah, it definitely reads like a cure for insomnia if you don't know what you're looking at. But beneath this dry academic phrasing is the foundational logic of how objects interact in our universe.
Right.
It is laying down the absolute ground rules for reality. And it's doing so with extreme, deliberate precision. I mean, every single word in this progression was chosen to systematically build a student's understanding from the ground up.
Okay, so the first major mandate of this text is where we really need to start before we can even attempt to understand the chaos of the real world, those falling coffee cups and swerving cars. The text insists that we have to isolate the variables.
Right, isolate them completely.
It says we must analyze motion based on the principles of conservation of momentum and impulse in one dimension. And that phrase, one dimension, is doing some massive conceptual heavy lifting here.
Oh, absolutely.
When I read one dimension, I immediately picture like a tiny bead on a perfectly straight, rigid, infinitely long piece of metal wire.
That's a great visual.
There is no swerving. There is no sidestepping. The bead can only slide forward or it can slide backward. That is the entire universe for this exercise.
Right. It isolates the movement entirely to the x-axis, just back and forth.
But wait, help me out here. If I drop my keys in the kitchen, they hit my shoe, bounce off at a weird angle, skid across the linoleum, and slide under the fridge.
A very familiar scenario.
Right. But by forcing me to use one dimension and think about a bead on a wire, aren't we just doing fake physics? Like, why am I learning rules that seemingly don't apply to the actual three-dimensional living room where I exist?
It's a fair question.
If the goal is to teach you about reality, starting by ignoring 99% of it just seems counterproductive.
What's fascinating here is that the text deliberately restricts the dimension not to ignore reality, but to make the underlying rules of reality visible.
Visible? How so?
Think about your keys dropping. When they fall, they are likely spinning, right?
Right, yeah.
Air resistance is pushing back on the irregular shape of the metal.
Yeah.
When they hit your shoe, the soft material of your sneaker absorbs some energy, and the angle sends the keys deflecting off in a new trajectory across the floor, where, friction takes over.
There's a lot going on.
There is just an overwhelming amount of noise.
Yeah, the noise is what makes it feel so chaotic and unpredictable.
Exactly. The text recognizes that if you try to learn a foundational concept, like the conservation of momentum, in a three-dimensional, messy environment, you will completely miss the lesson.
Because you're too busy watching the keys spin.
Yes. You'll be distracted by the spin, the friction, the angles. So by forcing the learner onto that single rigid wire, by stripping away the noise of multi-directional movement, The text ensures that you can see exactly what happens to the momentum.
Oh, I see. You essentially trap the momentum in a hallway where it can't hide.
You give it nowhere to go but straight ahead or straight back.
Yeah.
It allows the learner to see that momentum and impulse aren't just random, fleeting occurrences. They are conserved.
Conserved. Okay.
The word conservation in this text is the anchor for everything else. Think of it like a closed financial system, a strict currency exchange.
Like a locked bank account.
Exactly. In that isolated one-dimensional space, you can easily balance the checkbook. You can clearly see that the momentum didn't just vanish into thin air. It was perfectly conserved within the system. The one-dimensional mandate is the absolute only way to make that transaction perfectly readable to someone encountering it for the first time.
Wow. Okay. That financial analogy actually makes the concept of impulse in the text click into place too. If momentum is the currency sitting in the bank account, then impulse is the actual transaction, like the transfer of funds from one account to another.
That is exactly right.
So we have established this perfectly clean one-dimensional wire. We know we are tracking a closed-loop currency exchange. But, I mean, what's the point of a wire with just one bead? The real test of the system is what happens when another bead is introduced and they inevitably crash into each other.
Yes. So we move from the theoretical principle to the physical event, the collision.
Right. The text dictates that we must use models to analyze inelastic and elastic collisions in terms of the conservation of momentum.
Mhm.
So we are still on our one-dimensional wire, and we are still balancing that checkbook of conservation. But now we're introducing two very specific types of crashes, inelastic and elastic.
Right.
But I have another sticking point with how this is phrased. It mandates the use of models. Why does it require a model? Like, if we were talking about physical collisions, why can't we just take two real things, say two little wooden toy train cars, put them on a straight plastic track, smash them together, and just watch what happens?
Like a practical experiment.
Yeah. Why this specific retreat into a model?
Well, the physical world, even when you simplify it to a straight track, is a very messy laboratory.
Yeah.
If you smash two actual toy trains together, what is the first thing you notice beyond the movement?
Well, the sound. You hear a loud clack or a bang.
Right. And sound is energy. Heat is energy. When real physical objects collide, even on a perfectly straight track, the physical materials vibrate, creating sound waves that travel through the air.
Okay.
The friction of the wheels generates microscopic heat. They lose energy to the surrounding environment. So if a student tries to measure the mathematical conservation of momentum by, weighing and timing real toy trains, the math won't perfectly align. The real world literally steals a fraction of the energy during the crash.
So the checkbook won't balance at the end of the experiment.
It won't perfectly balance because some of the currency fell off the table into the realm of sound, heat, and structural deformation.
That reality tax we talked about earlier.
A reality tax, yes. If we connect this to the bigger picture, the text highlights models as a way to create a perfect intellectual vacuum for learning. In a mathematical or computer model, you can perfectly isolate the concepts without the environment taxing the transaction.
That makes perfect sense for isolating the two types of collisions they mention. In a model, you can simulate a perfectly inelastic collision like two balls of wet clay hitting and merging into one lump without losing any unexplained energy to the room.
Right, they stick together perfectly. Or you can program a perfectly elastic collision where two billiard balls bounce off each other with absolute, lossless mathematical perfection.
So the model isn't some, cheap substitute for a physical experiment. It's actually a purified version of it.
Exactly.
It's the only place where the rule can be observed in its absolute purest state. The text requires models because it wants to prove to you that regardless of whether a collision is elastic or inelastic, the rule of conservation never ever breaks. The model is the proof of the standard.
Well said.
Let's spend a second on the real-world implications of those two types of collisions, though, because understanding the difference between elastic and inelastic is huge for understanding how we design things for safety.
Oh, is it the difference between a minor fender bender and a catastrophic accident?
Right. If cars were built to have perfectly elastic collisions, like giant metal billiard balls crashing into a wall, it would mean you bounce back with nearly the same speed you hit it.
Which would be terrifying.
Exactly. The momentum would be conserved, sure, but the sudden, violent change in direction would be devastating to the people inside. Instead, engineers design cars with crumple zones. They deliberately make the car crash in an inelastic way.
Yeah, the front of the car crushes, deforms, and absorbs the energy. It essentially ties up the momentum in the destruction of the metal rather than bouncing it back at you. The model allows you to understand those extremes so you can engineer for the middle ground.
Which brings us to the final and honestly definitely the most complex layer of this text. We've set up our pristine one-dimensional track. We've agreed to use isolated, perfect models to watch these elastic and inelastic collisions.
Right.
But just observing the bouncing and sticking isn't enough. The text demands that we upgrade from watching the model to actually calculating its underlying mechanics.
Observation gives way to mathematical proof.
Yes. Here's where it gets really interesting. The standard says we must use mathematics and computational thinking to analyze the relationship among impulse, momentum, and Newton's third law.
Mm-hmm.
The phrase that immediately jumps out to me is computational thinking. They didn't just say do the math. They didn't say solve for X. They chose computational thinking.
It is a very modern, very deliberate choice of vocabulary for an academic standard. It really signifies a shift in how we want minds to process information.
Yeah, when I hear computational thinking, I immediately compare it to programming the physics engine for a video game.
Oh, that's a perfect way to look at it.
Right. When a developer builds a digital world, they don't just draw a race car or a bouncing ball. They have to write the algorithmic rules that tell the software how those objects must behave under any circumstance.
Exactly.
Like if your digital character throws a digital rock at a digital window, the game's engine has to compute the impulse, update the momentum of both objects, and decide dynamically what happens in the next frame. You aren't just solving a static math problem on a chalkboard. You are writing the dynamic underlying code that dictates reality in real time.
That is a brilliant way to frame it. Computational thinking is about algorithmic logic.
Yep.
It's about understanding the sequence of events, the dependencies, and the absolute rules that govern them. You are literally defining the if-then parameters of the universe.
Right.
And this raises an important question. Why does the text specifically require us to use this algorithmic computational thinking to analyze the relationship between impulse, momentum, and Newton's third law? Why are those three specific concepts grouped together into one package deal?
Yeah, that jumped out to me too. The text treats them as an inseparable trio.
Because they are the core engine of mechanical interaction. You cannot truly program a physical model without linking all three of them.
Okay.
The text is forcing the learner to see that these aren't just three separate vocabulary words to memorize. They are a continuous, unbroken algorithm. Because Newton's third law dictates that the forces mirror each other perfectly, tracking the momentum becomes a closed loop.
Every action has an equal and opposite reaction. So the action and reaction are the rules of the transaction.
Yes.
So if the third law provides the foundational rule that the forces are mirrored, how do impulse and momentum actually function within that loop? Let's go back to our video game engine analogy. If I'm writing the code, how am I defining impulse versus momentum?
Okay, so momentum is the state of the object. It is the mass of the digital rock multiplied by its velocity. It is the data point your game engine is tracking from frame to frame.
Okay, got it. The current state.
Right. And impulse is the active mechanism of changing that state. It is the force applied over a very specific amount of time during the collision.
Ah, that relationship between force and time is the real secret to how impulse works, isn't it? It explains why dropping a water balloon on concrete shatters it, but dropping it on a trampoline doesn't.
That is a fantastic example. The change in momentum is exactly the same in both scenarios.
Yep.
The balloon falls, it hits a surface, and it stops.
Same exact momentum change.
Yes, but the impulse is what dictates the survival of the balloon.
Because the trampoline stretches out the time of the collision.
Exactly. The trampoline drastically increases the time it takes for the balloon to stop. And because the total impulse required to stop the balloon is a fixed number based on its momentum, increasing the time drastically lowers the force applied at any given millisecond.
Oh, wow.
The concrete, on the other hand, stops the balloon almost instantly. The time is near zero, which means the force spikes massively, breaking the rubber.
This goes right back to the car crumple zones and airbags we talked about earlier. An airbag doesn't magically erase the momentum of a car crash. I mean, the crash is happening regardless.
Right, you can't cheat physics.
What the airbag does is stretch out the time it takes for your head to come to a complete stop. By adding just a few extra fractions of a second to the collision, it radically lowers the force of the impulse on your body.
It alters the variables within the algorithm to produce a survivable outcome.
Man, that's amazing.
And this is why the standard demands mathematics and computational thinking. Because that is the absolute only language capable of revealing how perfectly intertwined time, force, and momentum actually are. You literally cannot compute the outcome of the model without using the third law to define the mirrored forces, applying the concept of impulse over time, and adjusting the final momentum.
Right. By forcing the learner to use computational thinking, the standard is essentially saying, don't just tell me what an airbag does. Prove to me that you can write the underlying code linking the force, the time, and the mass together. It is moving the learner from being a passive observer of a car crash to an active programmer of the physical model. If you can use computational thinking to analyze that relationship, you haven't just memorized a textbook chapter. You have gained the ability to predict the future state of those objects with absolute mathematical certainty.
It gives the learner predictive power. You are no longer guessing what might happen. You are calculating what must happen.
It is incredibly empowering when you look at it through that lens. What started as just a dry, overly academic sentence is actually an invitation to write the source logic of reality.
It really is.
So what does this all mean? When we zoom out and look back at this short stack of source material, this excerpt on principles of momentum, impulse, and collision dynamics, we aren't just looking at a checklist for a midterm exam. We are looking at a brilliant, methodical progression for dissecting the universe.
Yeah, it operates as a blueprint for peeling back layers of complexity, step by logical step.
First, it forces us to set up a clean, one-dimensional stage, our single bead on a wire, so we aren't overwhelmed by the friction and the deflections of the real world.
Right.
Second, it asks us to use purified models to simulate both bouncy, elastic collisions and sticky, inelastic ones, proving that the currency exchange of momentum always balances.
Never fails.
And finally, it hands us the modern tools of computational thinking, asking us to stitch impulse, momentum, and Newton's third law together into an unbreakable algorithm. It teaches us how to take an overwhelmingly complex, chaotic reality and break it down into fundamental rules that simply do not break.
Which, leaves us with a fascinating paradox to consider.
I like a paradox. What is it?
Well, throughout this entire deep dive, the source material is focused entirely on computational thinking and mathematical conservation within a perfectly isolated one-dimensional model. We spent this time discussing how clean, predictable, and algorithmic that system is. But you started this entire conversation by talking about the messy, chaotic reality of dropping a coffee mug on the kitchen floor and dodging potholes in traffic.
Yeah, the three-dimensional soup. The
Well,
noise.
Right. So here is a final thought to mull over, building on the text's unwavering insistence on perfect mathematical conservation. If the fundamental laws of momentum, impulse, and action-reaction are mathematically perfect, algorithmic, and completely conserved on that simple one-dimensional line,
Yeah.
does the unpredictability and chaos of our daily lives stem from actual fundamental randomness in the universe? Or is the universe still functioning with the exact same perfect computational rigidity as the textbook model, and the chaos we perceive is merely our own human inability to computationally track millions of dimensions, variables, and impulses at the exact same time?
Oh.
Maybe your falling coffee mug isn't chaos at all. Maybe it's just a perfectly conserved, entirely predictable equation that is simply too complex for our brains to render in real time.